Today's paper is Informative Dropout for Robust Representation Learning, a Shape-Bias Perspective. The paper proposes a lightweight, model-agnostic method called Informative Dropout that reduces general texture bias of any CNN-based model. Through extensive experiments, the authors show that InfoDrop achieves consistently non-trivial improvement over multiple baselines in a wide variety of robustness settings. One of the intriguing properties of CNN is in its texture bias, meaning CNNs are biased towards texture instead of shape. Recent works reveal that the CNN models rely more on textures than structural information. For example, given an image with a cat's shape with elephant's texture, the model tends to classify the image as an elephant instead of a cat. Also, the CNN models are vulnerable compared to human visual systems. The trained CNN model often have trouble generalizing across different distributions between training and test dataset. Random image corruptions can also considerably degrade model performance, and it is often defenseless under well-designed image perturbations. The proposed informative dropout aims to reduce texture bias by decorrelating each layer's output with less informative input regions. The method is similar to the dropout algorithm. Instead of dropping out neurons in random regions, the InfoDrop algorithm zeroes out output regions with less information. The InfoDrop algorithm is only used during training, and it can be used without it during inference. To zero out an output neuron with less information, the authors model the dropout coefficient R of the jth neuron in the output C channel with a Boltzmann distribution. As shown in the equation, Pj with superscript L-1 is the patch in the input related to the computation of the output CCj in layer L. In the formula, I denotes self-information and T is the temperature. When value of I is low, the corresponding neuron is likely to be dropped, and the network tends to rely less on Pj L-1. The temperature T serves as a soft threshold of information. When the value of T gets small, the threshold lowers down, and only patches with least information will be dropped. On the other hand, if T goes to infinity, all neurons will be dropped with equal probability and the whole algorithm becomes regular dropout. In order to estimate I in the equation, a concept of self-information in Shannon's work is borrowed. Here, by considering input patch Pj as a random variable, Qj can be seen as a distribution which Pj is sampled from. Now, to approximate Qj, the authors assume that Pj and other patches in its neighborhood comes from the same distribution P. The neighborhoods here means local region centered at Pj with a Manhattan radius R. These neighborhood patches are taken as samples and Qj is approximated with its kernel density estimator Q hat j. Now, the information of Pj is estimated by the equation in this way. This method ensures amount of information in Pj by checking out its neighborhood patches. If Pj is more different from neighborhood patches, it means that it contains more information. For regions of solid color or high-frequency texture, neighboring patches will be similar, thus resulting to having a little information. The pseudocode shows the algorithm of InfoDrop. First, each output set, which denotes jth neuron in cth channel dimension, is calculated. Once obtained an output features, we iterate through each channel dimension C and calculate j with the dropout probability given by the equation 1, and zeroes out neurons that contain little structural information. Performance of InfoDrop is experimented under 4 different tasks: domain generalization, few-shot classification, robustness against random corruption, and adversarial robustness. Here, we'll just go through the results of domain generalization and few-shot classification task. The first table shows performance of InfoDrop on domain generalization task. As shown in the last row, baseline model with InfoDrop is more robust to the distribution shift between different domains and obtains consistent improvements over all target domains. The second table shows the result of InfoDrop on few-shot classification task. On all three baseline models, the use of InfoDrops improves the robustness universally. Lastly, the figure shows the comparison of saliency maps when using vanilla CNN and InfoDrop module. The leftmost column shows the saliency map of the vanilla CNNs, and images in the next column show the saliency map when using InfoDrop module. As we can see, structural information is captured better compared to the vanilla CNN version. Also, in style transfer task, InfoDrop mainly renders edges and content image, while texture or color tone is less affected. This is better shown in the first row example. While the tone of a person is mainly transferred in vanilla CNN version, the use of InfoDrop lets the model concentrate more on the structural information. Link to the paper and some useful resources will be provided in the description. That's all for today, and I'll see you next time with a new paper.